Welcome everybody to tonight's novice meeting for November of the Houston Astronomical Society. My name is Chris Morissette. I'm the novice chair, and we have the pleasure of hearing a presentation from Peggie Mueller, and I'm getting my teleprompter up here, so don't pay any attention to me reading off my phone. But Peggie's topic for tonight is called The Birth of Stars, Unraveling a Cosmic Conundrum. And I'm going to just be reading off of my teleprompter here, so just bear with me. It is now well accepted that stars form from clouds of gas and dust that collapse under their own gravity. However, if angular momentum of the collapsing cloud was not removed during its formation, the young star would spin up so much that it would ultimately tear itself apart. Nevertheless, there are young stars rotating at a fraction of their breakup speed. How can we explain this conundrum? After an overview of the early stages of stellar evolution, this talk will focus on how we, and Peggie will tell us more about who was involved, tested one of the explanations for this puzzling observation and share what we learned. A little bit about Peggie. Peggie has been a member of HAS since 2021. Her interest in astronomy deepened in 2016 after taking modern astronomy as part of a Master's of Liberal Arts program at Rice University. Under the mentorship of Professor Chris Johns-Krull, Peggie developed her capstone project, which led to a published paper entitled Tests of Disk Locking in T Tauri Stars of the ONC. And I'm hoping Peggie will tell us what ONC is during her presentation. And I think this was published in the March 2024 Astrophysical Journal. So tonight's talk will draw from their research, offering insights from her project and ongoing engagement in astronomy. So with that introduction, I'm going to turn it over to Peggie. So I'm going to stop sharing my screen, Peggie, and you should be able to share yours. And as you do that, let me just state as a reminder, if you have questions during the presentation, go ahead and put them in the chat. And then I will come back at the end and we'll go through a Q&A. If you would also mute your microphone, and then that way Peggie can go uninterrupted. So with that, Peggie, I'm going to turn that over to you. Thank you.
Sure. Let's see. I'm going to try. Maybe I'm not. That shouldn't work. Anyway, hi, everybody. Thanks, Chris, for the introduction. And I'm excited to be here and to share kind of some of the things I've learned under my advisor, Professor Johns-Krull at Rice. The star that you see on my first slide is V1331 Sig. It's a newly born star, although it's 1.5 million years old, but we call it an infant because it's going to live for billions of years. This is kind of what our sun might have looked like at 1.5 million years. One of the most puzzling problems a young star like this faces is how to manage its spin velocity. It turns out that these young stars spin much more slowly than they should if they were to conserve all their angular momentum. In fact, if they were to conserve all their angular momentum, they would spin up so fast that they would tear themselves apart, and we wouldn't need a Houston Astronomical Society. We wouldn't be around. So astronomers have recognized this conundrum since the 1960s. So it's been around for a while, and we're still working out the details of just what slows the spin of a T Tauri star or a very young star so that it doesn't tear itself apart. So we're going to start tonight by looking at just a quick overview of where stars form and then how they form. And then we'll review the mechanisms that have been proposed to slow their spin with a focus on a mechanism called disk locking. And by the way, the ONC in the title that Chris referred to in the paper is the ONC is the Orion Nebula Cluster, which is where we studied the stars. Okay, let's see. Why is my slide not progressing? I think I'm going to have to do this differently. No, okay. I got to change things around here. I don't know. Oh, there we go. Good, it worked. Okay, so of course, this is a disk of the Milky Way. Not too long ago, I thought the space between the stars in the Milky Way galaxy was empty, like a total void, total vacuum. But in fact, there's stuff between the stars, and we call that stuff the interstellar medium. So the ISM, which is short for interstellar medium, easier to say, is mostly composed of hydrogen gas. There's helium gas and other gases as well. And there's also these really tiny grains of dust, which are really important, actually. What you're seeing in this particular image, the dark clouds, that's part of the interstellar medium that's really dense, and that's where stars are born. We're going to zero in on the galactic center. Okay, here we are. And there's three things I'd like you to notice about this slide. That the first one is, if you look carefully, well, you don't even have to look carefully, pretty much you can tell that there's a lot of turbulence going on in the interstellar medium. It looks like it's getting blown around. In fact, last Friday at Larry Mitchell's talk, he mentioned that some of the open clusters get blown apart by this turbulence. So it's pretty strong stuff. The second thing I want you to notice is how different the density is. Most of the interstellar medium has about 1 atom per cubic centimeter. Compare that to our air, which has like 10 to the 19th atoms per cubic centimeter. So it's very, very low density. The denser parts, though, these really dark, see if I can get my cursor to come back over here. Here it is. These really dark clouds are the densest areas, and we call those molecular clouds or nebula. And those are the clouds where stars are born. So the third thing I want you to notice are these pink spots. And of course, this is the Lagoon Nebula. It's a vast area of interstellar gas and dust. And it's an area where stars are being born. And we know that because of that pink light. That pink light is made from the ionizing, intense UV radiation that's ionizing the hydrogen gas around those stars. And it's causing the electrons to jump up in energy level. And then when they fall back down, they emit a wavelength of light that we perceive as pink. And we actually call that specific wavelength of the hydrogen atom H alpha. And then, of course, there's H beta, H gamma, H delta, et cetera, of higher and higher frequencies. The Trifid Nebula is right here. You can barely see it, maybe. But the pink part, once again, is where new stars are being born. The blue part is a reflection nebula where the light, especially the blue wavelengths of light from the stars within that cloud, are getting scattered. Just like the light in our sky gets scattered and we see a blue sky, we see the blue wavelengths here. All right, so we are going to beam ourselves up above the disk of the Milky Way and look down on it. Now, we don't have any actual pictures looking down on our Milky Way, but we can look at a look-alike galaxy, the Whirlpool Galaxy, M51. Beautiful grand design spiral galaxy, and probably it's actually a little bit smaller than our own Milky Way galaxy, and the center isn't quite as barred. But you will notice that, whoops, we went ahead. You will notice that the stellar nurseries, all those little pink dots are where stars are being born, and they trace those spiral arms. And you might want to know why they're concentrated in the arms. And that is because those arms are density lanes, areas of higher density. So when the ISM, when the interstellar medium moves through those lanes, it gets trapped in that higher density area and it gets compressed, and that can trigger star formation. I think the next slide is kind of a indication of how that happens. So we have our cloud of gas and dust. It intersects a spiral arm, higher density, it gets compressed, stars get formed, and then it keeps moving right on through. So if we look at another, this is Whirlpool Galaxy again. Another place that stars are being formed are where this spiral arm is interacting with this dwarf galaxy, which is NGC 5195. So all kinds of triggers can cause star formation, not just spiral arms. There's other things. Something that kind of caught my interest is our own solar system has gone through spiral arms like 20 times in its past. And they think the last time it might have gone through one was like 65 to 70 million years ago, which is, of course, when we were at the end of the Cretaceous period and dinosaurs became extinct, which kind of makes sense because if these spiral arms concentrate objects, maybe asteroids and comets and big things that might hit into the Earth, more commonly might get trapped there as well. So I think that might be cool to kind of look back through time and see when all the different extinctions occurred and if we could have been in a spiral arm at that time. Okay, so we want to zoom in on one of these molecular clouds and just see what a stellar nursery looks like. Of course, the iconic image of the Pillars of Creation, I think, is one of the most beautiful stellar nurseries. It's in the Eagle Nebula, which has many stellar nurseries in it, actually. It blows my mind that this is 30 trillion miles tall. I can't even wrap my head around what 30 trillion miles looks like, but it's a gigantic, actually it's small by molecular cloud dimensions because many of them are much bigger than this. We can't really see a lot of the stars that are being born in here because of these dense clouds that are opaque to the light coming out of the stars. But we can go down to the Small Magellanic Cloud. This is the N90 star forming region. And these really hot O and V stars are emitting radiation pressure that has eroded away the clouds. And so we get to peek inside and see what's going on inside the stellar nursery. And notice that this stellar nursery is 150 light years across. So a lot of variation in sizes. Okay, so we've looked at where stars formed, or at least a few places. Now what we want to do is look at how they form. So we have this gigantic molecular cloud, and there's two primary competing forces in that cloud. There's a pressure gradient from the gas that's trying to expand the cloud, and then there's a force of gravitational attraction between the particles that's trying to collapse it. For millions and millions of years, this cloud can just hang in there, and those two competing forces will just be at mostly equilibrium. But if there's a trigger, like it goes through a spiral arm, or it intersects another galaxy, two galaxies collide, or maybe there's a supernova that the shock wave intersects this cloud, that can trigger star formation. And so what will happen is the gravitational attraction will take over and start to collapse the cloud. Now, the particles that are above, that kind of are along the axis of rotation, have nothing to support them. So it actually collapses into a disk. And that disk continues to collapse and rotate. In fact, it rotates faster and faster to conserve angular momentum. What's happening in this disk, though, I can get my cursor back, the particles are moving towards the center as it's collapsing, and eventually a really dense core forms in there. And that core also gets very hot because the gravitational contraction releases thermal energy. Okay, so to continue the story, we go to the next slide. And you can see our ice skater up there. That's the classic demonstration of conservation of angular momentum. And she pulls her arms in, she spins faster. And so here we have our original molecular cloud. It's flattened into a disk. It continues to contract. The center continues to get hot and dense. And here's where the conundrum starts. Because of the collapsing disk, the angular momentum should get much, the angular momentum will increase a lot. there's also accretion from the disk. So the disk material has angular momentum that's accreting onto the star, which increases the angular momentum of that protostar. We actually can't see that star. It's hidden behind opaque clouds, and it's only emitting at infrared, and those clouds will not let those photons through. So we haven't really been able to study what's going on in there, but we do see indications that there's accretion. Okay, it's spinning and spinning. It should fly apart, but it doesn't. That's the question. Where does the angular momentum go? But it keeps collapsing along, and that protostar keeps getting hotter and hotter until we can finally see it. And at that point, we call it a T Tauri star. And that's the stars we're going to be talking about the rest of the evening. So the material in the disk continues to accrete onto the star. If there's enough material, it'll actually accrete onto planets, and we'll have planet formation. Some of the disk material will be flung off by magnetic field lines. Some of it will just dissipate into space, and eventually that disk will be gone, and we'll have a T Tauri star without a disk. And then eventually, this star will have enough heat in the core that it'll ignite hydrogen fusion, and we'll have a sun. So the light from the star here, the T Tauri star, is really mostly from that thermal energy of the gravitational collapse. All right, to really understand where our T Tauri star in its evolution, we will go to a HR diagram. And we probably are all familiar with this, but I'll just review it in case you've forgotten it from your 8th grade science class. On the x-axis is the surface temperature, and it's increasing to the left. So the hot stars are on the left, the cool stars are on the right. And then the luminosity in solar units is on the y-axis, increasing toward the top. So here's our sun, and of course it's a G star. It's about 5,700 Kelvin on its surface, and of course 1 solar unit. And it falls on the main sequence. And remember, the main sequence stars are all fusing hydrogen in their core. Notice where our T Tauri star is. It's above the main sequence, so we call it a pre-main sequence star. It has more luminosity than our sun. So it's above the it's above the main sequence, and it's a little bit bigger. So I drew that. This is not to scale for sure, but it is a little larger than the sun. We're going to zoom in on this Hayashi track so we can see what's going on there. And these are actually birth lines or lines of evolution. This is our T Tauri star. As it goes down this evolutionary track, it is contracting, and so the luminosity is decreasing. Also, I think this is kind of weird, the temperature stays about the same, and that is because it's a convecting star. So any heat that's generated in the core gets carried away from the core to the surface and just keeps circulating to keep the surface temperature about the same. I've tried to kind of blow it up over here. So our T Tauri star does not start fusing or getting hotter and hotter to fuse hydrogen fusion until it's about 10 million years old. Now, it can happen sooner than that, but 10 million years is really the oldest that a T Tauri star can be, pretty much. And then the birth line kind of takes off in this direction, so the temperature rises, the luminosity rises, and then eventually we have a sun-like star. Notice, I mean, this is just kind of curiosity. These are birth lines. So if we have a star that eventually becomes 100 times the mass of the sun, it only takes 10,000 years to get to the main sequence. Whereas our star, our T Tauri star, which is about the mass of the sun, can take up to 10 million years to get there. So the larger, the more massive the star, the faster it gets to the main sequence, and really the faster it burns out. Okay, so let's look at a beautiful image. I don't know if you guys have seen this before, but I think this is just a spectacular image of a T Tauri star. This was taken in radio wavelengths. You would not see this detail in the disk with optical wavelengths because the disk is cold, or relatively cold, and the light is coming from the dust that's radiating pretty much in the either radio waves or infrared waves. This was taken by ALMA, right, in Chile. And this was in 2014. There's all kinds of images like this now. And modeling has shown that planets can be being made right in these dark lanes, even though this star is only 1 million years old, really early in the lifetime of a star. I think this kind of shocked people that planets could begin to form so early. Okay, so we've been talking about T Tauri stars. I think it's about time I tell you what they are. Some of you are variable star observers. And back in 1945, there was a man by the name of Alfred Joy who liked variable stars too. He was looking at 11 specific variable stars in Taurus, and he noticed that they were very different than the other variable stars he had looked at. So he proposed that these stars should be in a separate classification, and he named them T Tauri stars after the prototype star. So these are some of the things he noticed, that they have irregular light variations. They're associated with dark or bright nebulosity. They have emission lines similar to the sun's chromosphere, and you just don't see that in a whole lot of variable stars, I don't think. Now, since then, we've learned that these are young stars. They're very low mass, kind of solar masses, and they often have this circumstellar disk or a protoplanetary disk because sometimes they form planets. So there are two types of T Tauri stars. I couldn't not put the Sneetches on there. The Sneetches, that some have stars and some don't have stars. Some T Tauri stars have disks and some don't. The younger ones will, well, I shouldn't say younger. Earlier in their evolution, they will have a disk. This disk will dissipate, and then they become a weak T Tauri star. And these are artist renditions. These are not actual images. So, and notice that they put with this weak T Tauri star, they put a planet in there. All right. So what do you do with this information? Some stars have disks, some don't. So Edwards et al. In 1993 took 34 T Tauri stars and plotted them on a graph. The x-axis has the log of their rotation periods. The y-axis has the infrared excess, and that infrared excess comes from the disk. So the optical radiation from the star is irradiated by the disk in infrared. And you can probably tell what this team learned from this, right? The T Tauri stars with disks had a rotation period of about an average of 8 days to make one complete rotation. The T Tauri stars had a range of rotation periods everywhere from about 1.5 days up to 8 or 9 days. Okay, so they said, aha, the disk must have something to do with slowing the spin of a star. It must have something to do with taking away the angular momentum. Okay, so we won't go into great detail about all this. I don't want to scare you, but I wanted to show you a couple things here. First of all, one of the just amazing paper by Xu et al. 1994 was a beginning of really detailed explanations of how this stellar breaking might take place. And I just took several papers, 6 papers, all the way to 2024. The whole point of this is back in early 1960s is when they first, at least the first time I could see that anybody mentioned that there were differences, that the spin rate was so slow. So we've been studying this for 6 decades, basically. Okay, so Xu et al. And Ostreicher and Xu, these are the two main papers I'm interested in you knowing about because these are the two models that we tested. So Xu et al. Says that the star's magnetic field interacts with the accretion disk, setting up torques that keep the star at a slower spin. And I have a graph or a figure in the next slide that'll explain that better. Ostriker and Shu, okay, same Shu, added to this theoretical model, they added some winds that carry away angular momentum from the disk. Okay, and then we have Matt and Purix. They say, you don't need disk locking. It's just accretion-driven winds can take care of everything. But then we had these several studies come out and say, there's no correlation period or no correlation between the rotation periods and the disk presence. So what does that tell you? Maybe disk locking maybe isn't a thing. And then Gallet said, okay, so these are basically, the magnetic field of the star is ejecting material, which is carrying away angular momentum, accretion-powered stellar winds carrying away angular momentum, so really no disk locking. And then CERN, and there's actually more papers than this, of course, but I think these are important ones. This was interesting because they're looking at the evolution of the rotation velocity and saying the intensity of the magnetic field and the fraction of the accretion flow that's ejected regulates the angular momentum. All right, so what do we do with all this? Well, let me first maybe clarify some of those, especially the Shu and the Ostriker and Shu. So this is our T Tauri star. The red lines are the magnetic fields of the star. The magnetic field lines truncate the disk. This is the disk. It's a Keplerian disk, which means that it spins faster here than it does out here. And those magnetic field lines truncate the disk in the inner disk at what they call the rotation radius. In other words, the material at this point in the disk is rotating at the same velocity as the star. And that's where the torques are set up that keep the star spinning more slowly than it would like to conserve its angular momentum. Okay, so what's happening is the ionized gas in this inner disk is being carried along by the magnetic fields, funneled onto the star, and it doesn't hit the star gently and nicely and quietly. It hits at hypersonic speeds. It creates a gigantic shock. The temperature above that shock rises to like 1,000,000 Kelvin. It's a tremendous show. I'd love to be able to see it. And then at the co-rotation, just outside the co-rotation period, rotation area, radius, the magnetic field lines are open. They don't close back to the star. So material is carried away by the magnetic field. And that's what Ostriker and Shu called X-winds. So I hope I did a good job with that. Okay, so now we want to see what the models look like that we're testing. Okay, so this model was derived by Johns-Krull, Chris Johns-Krull, my advisor, and his student April Gafford in 2002. And look how simple it is. It's a proportionality. It's a relationship. And to test this, you need the radius of the star. You need the mass of the star. You need the mass accretion rate of the star and the rotation period. And if you can come up with those parameters, you can see what kind of how strong this relationship is. The assumptions are what's really important here. So they're assuming a consistent magnetic field strength from star to star. Chris happened to be a magnetic field expert, basically, and he stands by this, that it's for T Tauri stars, it is pretty consistent. The second assumption, dipolar magnetic field, just means it's kind of like the Earth, right? There's a north and south pole. This is absolutely not true. There is a dipolar part to it, but it's actually much more complicated. And then, of course, we're assuming disk locking, which is what we're testing. Okay. The second model, we only tested 2, looks like this. Okay, it's also derived by Johns-Krull and Gafford. Same assumption here, consistent magnetic field, dislocking, but Chris found a way to take the model that Ostreicher and Shu came up with and modify it. And he modified it by adding this term to the proportionality. That term is called the filling factor. And it's basically the percentage of the stellar surface that's affected by the accretion flow. Remember, I told you this accretion flow makes a huge shock at the stellar surface, and UV, soft X-rays, it's really heated up to high temperature. So that's an important part, really, of this whole model. Okay, so all we have to do now is find values to put in those proportionalities. Not easy, but we tried. And we chose 33 stars in the Orion Nebula cluster because it's relatively close. The stars are really young, 1 million years old. It's very well studied, so we could actually get rotation periods from the literature. And there's mostly an unobstructed view. And I know you've all seen this. It's just a gorgeous view of the Orion Nebula, the trapezium stars, those really hot stars are in here. And they, over time, they've blown away the clouds, right? And we see this pink color that, remember, is H alpha because of the intense radiation of those stars. I just think it's a beautiful nebula. It's my favorite nebula, can you tell? Okay, so now we're going to put it kind of all together. Okay, you can laugh at this because this is definitely not to scale. T Tauri stars are not as big as the interstellar medium, and my computer is not as big as the Hubble Space Telescope. Sorry, but I had to squeeze it all on one slide. So what we have here is some infrared radiation going through the interstellar medium. And by the way, the interstellar medium isn't nice. I mean, we've already pointed this out, right? It's not nice and uniform like that in density. It has a high variability of density. So knowing how dense it is, where your photons that are hitting your spectrograph are coming from, is close to impossible. Okay, so here's my accretion starting to be funneled down to the stellar surface along magnetic field lines. Oops. It hits the surface. There's that big shock. Now, this is real important to remember because the region above the shock is heated up, really high temperature, right? And we are going to model that. We have to model that because that's the extra radiation that we wouldn't see in a T Tauri star that didn't have accretion. Okay. All right. So once that happens, there's UV. Oops, I went too far. Let's go back. UV radiation. Notice what happens to the higher frequency radiation. It gets scattered, just like our sky scatters it. And so that's a problem because what happens then, the spectrum that we get is actually cooler than it should be, right? So we have to correct for that, which is a bit of a guessing game because we don't really know how the nebulosity changes, how the density of it changes in that interstellar medium. Okay, so there are problems. It is not an easy thing to do. But for those of you that are true novices, I put in 2 slides just to explain what a spectrum is. So if we have a hot, dense object, and there's nothing between that and our prism, we get a nice, beautiful, continuous spectrum. However, if there's a cloud of hydrogen gas that's much cooler, maybe it's the atmosphere of the star, maybe it's the interstellar medium, the radiation from that hot, dense object going through the cloud, the atoms, the hydrogen atoms in that cloud will absorb specific frequency of light. And that light will not be in our continuous spectrum, and it'll be just dark lines where that light has been taken out. And by the way, this is H alpha that makes that pink color in the stellar nurseries. Okay, on the other hand, if this cloud of gas is hot, and maybe it's hot because UV radiation is being given off by a nearby T Tauri star, then the atoms of hydrogen in that gas the electrons will be energized, they'll jump up a level or 2 or 3. When they fall back down, they will emit specific wavelengths of light. And once again, we have hydrogen alpha, but now instead of it not being there, we actually see that wavelength of light. Hope that made sense. Okay, so here we are putting it all together. Whoops. Here's our T Tauri star. Here's our electromagnetic radiation. Here's our Hubble telescope with the STIS spectrograph, giving us a one-dimensional spectrum that we can turn into a two-dimensional spectrum. And we did not get data out to H alpha, which is 656 nanometers. We got H beta, which is 480, I'll say this right, 486 nanometers, and then H gamma and H delta. Okay, so these are 2 examples of our spectra. Weak T Tauri stars here and a classical T Tauri stars here. You can see a significant difference, right? This doesn't have any emission lines. There's no accretion going on here. There's no intense UV radiation given off. But here we have beta, gamma, delta, and then this is low resolution spectrum, so a lot of the lines kind of run together down in here, and we have our Balmer jump. Okay, so how do we get the radius and mass and all those parameters we need? Well, we start with our observed spectrum. This is probably the best spectrum I got out of all of them. And we use the weak T Tauri star spectrum as our photosphere with no accretion. Okay. We model, remember that slab of hydrogen gas above the shock. We model that as a hot hydrogen slab using a temperature, an electron density, and the length of the slab. Do we know those numbers? Not really, but we have a pretty good estimate of them. If we add that hot hydrogen slab, the excess radiation from the T Tauri star, to the stellar photosphere, we get a really good fit model. And we have a Marquette fitting routine that takes all our parameters and varies them over 100 times to get the best fit model that it can come up with. Okay, now you can see there's a big difference between the stellar photosphere, which has no excess accretion on it, and then ours. There's a lot of excess accretion. So we use that difference to figure out what the mass accretion rate is and some other parameters. Okay, I don't think I need to go through this. I'll if somebody has a question later, this is just telling you where all those variables come from. So just briefly, we have to calculate an accretion luminosity that we use in our to get the mass accretion rate. Okay, if we need to come back to that, we can. Okay, and once again, I don't expect you to be able to see this. This is my 15 classical T Tauri stars, and these are the parameters that we calculated from them. Now, I will say that the rotation periods we got from literature. I don't know if I said that before, I meant to. Okay, here's our first model. And you can see that the fit is not very good. Let me see, I got my glasses on for this, sorry. We have a correlation coefficient of 0.22, and a good correlation coefficient would be 1. That would be a 1-to-1 relationship. Our false alarm probability, which tells us how much we can believe in our correlation coefficient, it should be less than 0.01, and it's 0.438, so that's not very good. And I guess I failed to mention this, but basically we're putting the left side of the equation on the x-axis and the right side on the y-axis. And these are our 15 classical T Tauri stars. I have JW1000 pointed out on here because it turned out to really skew. When you only have 15 data points and one of them is kind of wacky, it really skews all your data. And if I take it out of there, it really changes things. Okay, so this was the model that assumed a dipolar magnetic field. The second model looks like this. This is the one that does not require a dipolar magnetic field because we added this term. And we now have, it's still not great, but we have a correlation coefficient of 0.52. And we have a false alarm probability of 0.046, which is not less than 0.01. So that makes it difficult to make any conclusion. It certainly looks like a better relationship. The slope of the best fit line is 0.7, which is, not bad. The dashed line is if the correlation was 1-to-1. This is how our best fit line looks. So we were a little disappointed, but we know we had some of our spectra were a little shaky. And we have this JW1000 star that just was a little wacky. So what we did, there had been 2 previous studies done under Johns-Krull. And so we combined, they were older stars. They were like 3, 4, and 5 million years old. Ours are 1 million. We were actually hoping to see if maybe we would see some evolution of the dislocking or something, but we didn't. But when we put all this data together, our correlation coefficient on this guy with the dipole field geometry is 0.006, really bad. And the probability, false alarm probability is 0.96, which is terrible. But then when we look at the model, the Ostriker and Shu model that he modifies, so no field geometry was necessary, specific geometry was necessary. We have a 0.82 correlation coefficient, and the false alarm probability is way low, 10 to the negative 15th. So combining the data really helped a lot. So we conclude that dislocking is a mechanism that regulates the angular momentum of an accreting T Tauri star, provided that the assumption of a dipole magnetic field is relaxed by using the filling factor as a parameter of the magnetispheric accretion model. Now, one last thing, which I think is really exciting. Oops, well, these are some questions. There's always more questions, right? And I put this on here because I think it's just such a beautiful JWST image of a protostar. Now you can't see the protostar because remember I told you it's in these opaque clouds and it only emits like an infrared or really long wavelengths, and they're trapped in there behind that opaque cloud. But what you can see is the light coming, and this is not optical wavelengths, this is infrared, JWST is infrared, right? Makes the dust around it, it shines off the dust so you can see the dust, and down here the dust is thin, so that light the blue wavelengths are getting scattered, so we see that blue color. Okay, this is the exciting slide, sorry. I just noticed this on October 4th, so just last month, the Max Planck Institute of Astronomy verified, they observed, they have an image, look at if I can get my cursor back over here. This is an image of the winds coming off the disk of a T Tauri star. It just blows my mind. So they actually claim that they confirmed that there is a magnetic field driven wind from the disk. There is a thermal wind from the disk, and there is an X wind from the disk. They actually observed the X wind in the model that we were testing. So I just got real excited about these little things. And by the way, those disk winds are really important because they take angular momentum away from the disk, which allows the material on the outer side of the disk to migrate in so that it can accrete onto the star and form that dislocking. Now, we haven't had any observations to confirm dislocking. So it's still a debated mechanism to take angular momentum away from the star. And that's my talk. I hope you enjoyed it.
All right. Well, yeah, Peggy, that was something. I'm glad we recorded this because I'm going to need to go back and let it soak in.
I'm
Um,
sorry.
no, that's quite all right. This is how you learn. So we have a couple of questions from Bill Spazzeri. I've got a couple myself, but I'm going to let Bill go ahead and take the floor. So, Bill, if you don't mind coming off of mute, and I'll let you go ahead and just ask the two questions on your own, if that's okay.
Thank you, Chris, and thanks for a great presentation. Absolutely, positively. Um, I'm sorry, I have a bunch of questions. Let's see. First of all, a high five to you and the professor that you worked with on putting this all together. My first question is, have you published or do you plan on publishing? Or did I miss that?
No, I think Chris mentioned it in the intro, but yes, we published it in the March 2024 Journal of Astrophysics, Astrophysical Journal, APJ.
Good one, good one.
A long time to get it in there, let me tell you.
You worked. You worked. You worked to get that, yes. And but I have to tell you, I've been giving presentations for 40 years. You do a great job on giving a presentation.
You're so sweet.
Anyway, congratulations on that. Also, one of my questions was, are there any other characteristics to T Tauri stars besides the fact that they're young and they're not on the main sequence yet? You definitely answered that one. But, and maybe you said this, I apologize if you did, but I got the impression that all stars go through a T Tauri phase before they get on the main sequence. Is that accurate?
No, not necessarily, because the more massive the star, I don't even know that they've confirmed exactly how their rotation period is controlled, if it's by accretion winds or not. So I guess it's hard for me to answer that. I haven't studied more massive stars. I mean, so T Tauri stars are 2.5 solar masses or less.
That's right. Okay.
By definition. So anything greater than that, I'm not sure how their evolutionary track. I know it's being studied. From what I've read, there's not a whole lot understood, but that was years ago when I first studied all this. So
okay, you said that before. It didn't sink in. In other words, the characteristics is they've got to be low mass, and a lot of stars are not. A lot of stars are not low mass. Okay.
Right.
By the way, I found this very, very interesting because I've been studying astronomy for 65 years, obviously and I know all about stars, right? I had no knowledge of this issue whatsoever. So this was a real eye-opener for me. Thank you very much.
Thank you.
All right, thanks, Bill. I'm going to go ahead and ask my questions, and these are just real basic questions, Peggy, because I just want to make sure I've got this clear. So you talk about the loss of angular momentum, and I'm an old mechanical engineer, but harking back to my days of college physics, if I remember right, the angular momentum is a function of the angular velocity and the moment of inertia, which really is kind of a way to say the mass of the item. So if the angular momentum is going to change, I mean, like in our ice skater example, you can change the rotational velocity of the ice skater without changing her angular momentum, because she can move her arms in and out, and that will change the speed, but the angular momentum hasn't changed. It's constant. In this case, you're truly talking about changing angular momentum, and in my mind, that would mean that there's a loss of mass. Am I getting that right?
That's a really good question, because that's the crux of things. So the angular momentum of the system changes. It doesn't change. What happens is, as the disk contracts, of course, it has to spin up to conserve angular momentum, right? Like the ice skater.
Right.
But it doesn't. If it were allowed to spin up to the speed necessary to conserve all the angular momentum through the evolution, it would speed up to about 300 kilometers per second and tear itself apart.
Mm-hmm.
And it doesn't. And so where does that angular momentum go? Well, we're claiming it goes to two places. Some of the angular momentum is lost from the disk wind, so materials taken off the disk.
So that would be a reduction in mass?
That's a reduction in mass.
Okay.
And the torque that's set up between the magnetic field on the star that connects to the co-rotation period of the disk.
Okay.
The torque on the star, so it can't spin up because it's forced to spin at the same velocity as the disk.
Okay. Okay. I think so. If it was a purely mechanical system, then the mass would be the only variable. But since you've got electromagnetic physics going on as well, you're saying that can have an effect on the torque. So I think I got that. And then the last question.
Yeah, it's not on torque. Yeah, sorry.
Just the last question, disk locking. Could you just give me, I'm not sure I understand 100% what you're talking about. Could you tell me what that means?
So I wonder if I can go back to that slide. I don't know if I can do that. Let's go back to, I forgot how far back it was. There it is. Okay. So the magnetic field of the star, the ionized gas in the inner disk is attracted to the magnetic field because it's ionized. Mm-hmm. And it gets funneled to the star and it crashes into the star, right? Mm-hmm. So the star is basically linked to the disk. And that's disk locking. The torques that force the star to spin more slowly because the disk isn't going to let it spin up. Mm-hmm. And actually, so that's disk locking right there. The torques that I don't know how I get out of this. I hate to keep going back and forth, but maybe this slide. Let me get there. Let's see. This slide. This is right out of the Ostriker and Shu paper. Okay. And I don't know how well you can see that, but I think it's a really good. And can you see it okay or not?
I can, yeah.
Okay, so you can see that there's mass coming from the disk to the star, and then there's angular momentum being carried back to the disk by those torques.
The electromagnetic?
Yeah. Okay. And yes. And then some of that angular momentum at least will be carried away from the disk through the open magnetic field lines. Okay. There's more disk material being taken off. Well, they have the X-wind way over here. There's more material taken off from the accretion disk further out by just winds and thermal winds, stuff like that. But so there's a lot of angular momentum, carried away from the disk so that it allows disk material to move in towards that X rotation period, radius. It's pretty complicated, but you might want to look up this paper, Ostriker and Shu, 1995. Okay. And I can send you a link if you can't find it, but yeah.
Sure.
Pretty complicated.
Good. Okay, so I appreciate that. Let me move on to some other questions. Eddie K asks, in a T Tauri solar system, can the angular momentum of the contracting star be transferred to protoplanets?
Probably does. I think they're just starting to study that. And, we don't have verification. I think it's pretty well accepted that there is accretion from the disk material onto the planet. And so any angular momentum from that disk material would be transferred to the planet. But beyond that, I'd have to hand it over to an exoplanet person.
Gotcha. Eddie K, is there any other questions that you had, or did that answer your question?
Yeah, no, that was great. Maybe a follow-up question would be, so if the angular momentum is transferred, could that explain the reason for why you, as the contraction happens, you don't actually get the spin that would equate to the star kind of falling apart because that angular momentum is going elsewhere?
Oh yeah, for sure. Absolutely. Yeah, the angular momentum is part of it is going elsewhere. Well, it's all going elsewhere for sure. Yeah, I think that answers your question.
Okay, that was all that we have in the chat. If anybody has, I'm sorry, we got one more from Mark Gordon. Why is this model limited to 2.5 solar masses?
So T Tauri stars by definition are 2.5 solar masses or less. And I think that's because they are what forms sun-like stars. So anything bigger than that is a different classification. I think they're called Herbig stars, and they behave a little differently, and they're much more massive. I don't know. That's probably not a great answer, but I don't know enough about Herbig stars to answer more fully. Sorry.
Did that answer your question, Mark?
Probably not.
Did you have a follow-up at all, Mark Gordon?
Can you hear me?
Yes, we can.
Yeah, that answer. And I also want to say great presentation, even though most of it went over my head. I'm glad you didn't dumb it down. It's good to see what serious research looks like, and even though I might not understand the details, seeing the concerns of serious research and the questions you have to answer, I just find fascinating. I think I got, for me, since the basics, I got more questions about your asides probably than your main research. Like, how do you know the last time we went through something was 65 million years ago? Or how do you know the age of a star by looking at it? And I suspect those are all just basic astronomy questions rather than what you're concerned with.
Yeah, so the whole solar system going through the arms of our galaxy was something that when I was putting this together, I started thinking, well, yeah, we would have moved through it. So I just did some research, and several papers agreed that we've gone through about 20 times through spiral arms in the history of our solar system. And then I started thinking, well, then we must have gotten bombarded, and somebody's paper or two or three said, yeah, it's probably about 65 million years ago when the dinosaurs. So I actually am more interested in looking into that a little more deeply myself.
I'd never heard that before, but yeah, that's absolutely an intriguing possibility.
Yeah, I think it's really intriguing, and I need to read more about it. But thank you. I have to tell you guys, I don't know, I had never studied astronomy in my life ever until I took this Master of Liberal Studies degree at Rice. It's like a nighttime thing, and I accidentally took an astronomy class. I was actually signed up for a different class, but it got full, and they put me in astronomy. And it turned out to be my favorite class of everything. And it just grabbed my attention. And I told Chris at the end we had to do a project. And I said, I'd like to do an astronomy project, but I don't think I have the math. Like, I was a geologist, okay? I don't have the math and physics background to do this. And I will give 110% to him for his patience. I mean, he taught me from the ground up, and took me out to McDonald. I got to use the 2.7 meter out there. Yeah, my whole life was changed.
No kidding. Wow.
Yeah.
Okay. Well, good for you.
Yeah.
We've got another question from Eddie K. He asks, if the star is too young for fusion, what causes the luminosity?
Yeah, good question. So the gravitational contraction of the disk because it's potential energy going to kinetic energy, right? It releases thermal energy. And as the contraction continues, the density of the core increases and the heat, the temperature of the core increases because of this thermal energy generated by the contraction. There's a second part to that gives some energy to that core or to that T Tauri star. There is some deuterium fusion, but I understand that's a very minimal amount of heat that comes from that. So it's mostly the thermal energy from gravitational contractions. Crazy.
So as you're contracting and getting, building up the pressure and the heat required to get to fusion, you're getting hot. So you're emitting energy that will register as luminosity. Is that
exactly?
All right.
Exactly. Thank you. Mhm.
Gotcha. Okay, well, listen, does anybody have any questions? I'll just open up the floor to any other questions before we close out for the evening. If you've got a question, please come off mute and ask.
That's a great job, Peggy. Thank you so much.
Thank you. Thank you guys for putting up with me. Like I said, I'm more of a novice than anybody here, and I'm really a visual novice, and I'm trying to get better, and I'm trying to do my astrophotography more, except I just have a camera. I don't have a telescope to do it through, but someday maybe I will.
All right. Going once, going twice.
Yay.
All right. Well, that's it. So Peggy, again, just to kind of echo the comments that you've received, thank you very much. This presentation was challenging, but I think that's how we learn. So we appreciate that. And like I said, I'm glad we recorded it because that way, at least I can go back and really dig into the material and get my hands or my arms around things. But wonderful presentation, and we really appreciate you presenting tonight and helping out the novice program. So thank you very much.
Oh, you're welcome. And you can email me questions, and I'll try to answer them if you like.
Perfect. All right. Well, with that, I'm going to close out the meeting. And again, everybody have a great evening. And thank you for joining tonight. I appreciate that.